Today we will be discussing about a different type of transistor which is known as field effect transistor. Earlier we have discussed about BJT or bipolar junction transistor, but today we will be discussing a different type of transistor which is different from the BJT, and this is FET. In short, it is known as FET and its full form is field effect transistor. So, the field effect transistor is also a 3-terminal device and it is a voltage control device. In transistor we have earlier seen that it is a current control device, but the FET is a device which is voltage control. And like a BJT, the FET also can be used as an amplifier and as a switch. And one important difference from BJT is that the FET is a unipolar device. That is, here the charge carrier is one type, either it is the holes or the electrons. But in BJT we have seen there are two types of charge carriers. It is a bipolar device. Now, the FET has been actually known since 1930s. The basic concept of the FET was developed in the 1930s, but practically this device was developed in 1960s. But since 1970s, a particular type of FET which is known as metal oxide semiconductor field effect transistor, or in short it is known as MOSFET, has been existing in a very popular way. That means we have seen that since 1970s onwards, this particular type of FET which is the MOSFET has been used immensely, and ultimately nowadays we find its application in VLSI circuits, that is very large scale integration circuits where you can assemble hundreds and thousands of circuits in IC. We find the application of MOSFET tremendously, and there are reasons for this ever growing popularity of the MOSFET. The reason being is that at first the size, the MOSFET transistors can be made quite small, and basically it occupies a very small silicon area on the IC chip. So, as it can be made on a very small area, so it helps in reducing the size of the chip. So, we can have a number of the transistors on a small area of the IC. So, this is one big advantage to designing smaller and smaller area devices, which is nowadays very popular. So, it finds its application from that point of view to be very popular. Another reason for growing in use of the MOSFET is that its manufacturing process is also simple. And another important factor which contributes to the use of MOSFET is that the digital logic and the memory functions can be implemented with circuits using only MOSFETs, and no resistors or diodes are needed. We can do away with the resistors and diodes, and we can build the digital logic as well as the memory functions only using only MOSFETs. So, these are the reasons why we see tremendous use of MOSFET in ICs nowadays. So, that is why the most of the VLSI circuits at present are using MOS technology, and we see applications of MOSFETs in microprocessors, memory chips, integrated analog ICs, as well as integrated circuits using both analog and digital ICs. Now, it is a symmetrical device. The MOSFET is a symmetrical device, unlike BJT. So, in BJT we have noted that the regions, emitter, base, collector, these regions are not symmetrical. That means we cannot interchangeably use an emitter and collector, but that is not so in MOSFET. In MOSFET, the two regions which are drain and source, as we will be finding later on, they can be interchangeably used. So, it is a symmetrical device. Now, we will be discussing about the different types of MOSFET. So, first of all, let us take up the enhancement type of MOSFET, that is most widely used FET. So, we will be first of all discussing about the enhancement type MOSFET, and then we will be also discussing about the depletion type MOSFET and the junction FET. So, let us first see the physical structure of an enhancement type of MOSFET, and we will be first of all taking up the N channel MOSFET. There are two types of enhancement type of MOSFET, which are N channel and P channel. So, we will be first of all discussing about N channel enhancement type MOSFET. So, here we see the structure of an enhancement type of MOSFET, which is N channel. So, here as we see, there is a P type of substrate, which is the body of the MOSFET, and there are two N regions. Here they are shown as N plus and N plus. Just plus is to mean that it is a heavily doped N region, and we will use minus for lightly doped N region. So, these two N plus regions as shown in this block, these are two N type doping materials, these are two N type materials, and the P type and N type semiconductors both are grown on a single crystal silicon wafer. So, here actually the P substrate and the two N type materials, these are N type semiconductors, these are grown on the silicon wafer, and as you see here, there is a silicon dioxide layer which is grown between the two N type semiconductors. That is, we have an insulating material which is the silicon dioxide. This insulating material is there between the two N type semiconductors, and on this insulator there is the metallic contact, which is the gate terminal. So, as you can see here, there is a gate terminal, which is the terminal taken out from this metallic contact, which is grown over this silicon dioxide. Now, there are other metallic contacts over these two n-type semiconductors. These two n-type semiconductors are known as the source and the drain. So, we have another metallic contact over the source region as well over the drain region, and the two terminals which are taken out from this source and drain regions metal contacts are the source terminal and the drain terminal. Now, there is another terminal shown from the body or the substrate, which is shown here as B. B is for the body terminal, and basically at this point we have 4 terminals, but ultimately we will be observing that this body terminal is connected to source terminal generally, and finally we will be having 3 terminals only. These are gate terminal, the source terminal and the drain terminal. So, here the in between the two n-type of semiconductors which are source and the drain, we are denoting this length as capital L. Basically this L is denoting the length of the channel. Now, what is a channel that we are going to study? There is another term which is width of the channel, and it is denoted by W. It means the width of this whole channel. So, now in this diagram what we see physically, as there are 3 regions, one is the P type, the other 2 are the N type regions. These are the main regions in the MOSFET, and these 2 regions which are source and drain regions, these are interchangeable as I have already mentioned. So, this device is a symmetric device. We can use the source and the drain interchangeably. There is no particular reason which should be source or the other should be drain. Now, this construction of the MOSFET, if we now see the cross sectional view of this whole construction, we will be having this type of diagram where we have this P type substrate having a body terminal taken out and the 2 N type of semiconductors, and in between these 2 N type semiconductors is the P type substrate, and on this region between the 2 N type semiconductors is grown the insulating material which is silicon dioxide as shown here, and on this, on the top of this silicon dioxide we will be having the metallic contact which is the gate terminal, as shown here. The gate terminal is taken out from this metallic contact which is grown over the top of the silicon dioxide, and similarly in the 2 N type regions which are the source and the drain, we are having the 2 metallic contacts out of which the 2 terminals source and the drain are taken out. So, we have now these 3 important terminals, gate, source and drain. Of course, this body terminal is just optional, that means we generally connect the body terminal to the source, but here we are just showing all the 4 terminals. So, this is the cross sectional view, and this oxide layer, that is the layer of the silicon dioxide, has a thickness which is denoted by T ox. T subscript ox means it is the thickness of the oxide material. Now, let us go into the basic operation of this MOSFET. It is an enhancement type MOSFET. Why it is called an enhancement type of MOSFET? Now, we are redrawing the MOSFET here, just simplifying the drawing by indicating the P type substrate, two N type semiconductors, which are the source and the drain. Here this is the drain, this is the source, and we have these three metallic contacts. Out of these three metallic contacts, we have three terminals: drain, gate and source. So, we have to notice it here is that these metallic contact from the drain, it is contacting to the this N type semiconductor, that is the drain, this is the source. So, this metallic contact is contacting with the source, and the gate terminal, which is having this metallic contact, as you can notice that there is no contact from the metallic contact of the gate terminal to the P substrate, because in between there is this insulator, that is the insulator is the silicon dioxide, which is in between the gate terminal and the P type substrate. So, this region is having this insulator in between, and we have this substrate terminal, SS for substrate, which is the P type, it is P type substrate. We have the substrate terminal or body terminal, as earlier we have denoted is the body terminal. This is the same thing, the substrate or the body terminal. Here this is connected with the source. So, basically we have these three terminals. Now, let us have VG as 0, that means we are not applying any voltage between the gate and source, we are keeping it open, but we are having a voltage VDS between the drain and the source, a positive voltage is applied. Now, what will happen if we are having this type of arrangement? Let us study. Now, you have noted that these two are regions or semiconductors which are rich in electrons. These N type materials, these are rich in electrons. They are having the carriers which are electrons. So, they have high concentrations of electrons. But we also have to note that in between these two N types, there is no channel. Although these two regions are rich in electrons, but still at this present arrangement, there cannot be any current flow between this drain and the source, because there is no channel present. Although there is a voltage being applied, which is VDS, what does this voltage do? Basically, this is a voltage which is making the two PN junctions reverse biased. If we notice this junction between the P type substrate and this drain, which is an N type semiconductor, this is nothing but a reverse biased PN junction. So, that will be having a high resistance, so there will not be any flow of current, as well as this PN junction also reverse bias. So, these two back to back PN diodes are basically having reverse biasing junctions. So, from this end to this end through this P if we travel, we have NP and again PN, both these diodes are reverse biased. So, we will be not having any flow of charge carriers, or we will be having zero current. There will not be any flow of current from the drain to the source. So, under this condition that the voltage from gate to source is 0, VGS is 0, and although there is a voltage which is positive between drain and source, this does not help in establishing any channel between these two N type semiconductors. That is, in between drain and source there is still no existence of any channel. So, channel is absent between these two N type semiconductors, and that is why there is no current flow or zero current at this stage. So, next let us see what happens when we apply a voltage between the gate to source, and that voltage is say positive. Now, we have positive voltages between the gate and the source and the drain and the source, both are positive voltages. So, here that we are showing by this VGS having a source which is having positive to gate, that means with respect to source it is positive. So, between gate and source we have a positive potential, and similarly from drain to source we have this VDS that is also positive, and typically this is the substrate terminal is connected to the source terminal. Now, what happens? Now, as there is this voltage between gate and source which is positive, so this positive terminal will be this repelling the majority charge carriers in the P type of semiconductor. That means, this positive potential at the gate terminal will be repelling the positive charges or the holes in the P type of the substrate. In the P substrate, the majority carriers are holes and the minority carriers are electrons. It is a P type semiconductor. So, as we are having a voltage which is positive at the gate terminal, so they will be repelling these positive charges to the deep inside the substrate. That means, it will be repelling to the right, it will be pushed towards deep into the P type substrate, and the electrons which are the minority carriers will be attracted by this positive terminal of the gate. So, they will be coming to left and they will be accumulating near the insulator silicon dioxide, that is they will be crowding just near to the insulating material which is present. So, as these majority carriers which are holes, they are pushed to deep into the P type substrate away from the insulator, and around this insulator there will be a depletion region, because in this region the acceptor ions will be just surfaced out, which are the immobile charges. If you recall, in a P type of semiconductor, the holes are the majority carriers, and here if we are pushing away the holes as these are being pushed away, they will be uncovering the immobile charges which are nothing but the acceptor ions, which are negative ions. So, that means there will be a depletion region near to this region where from they are pushed away, the holes are pushed away. So, this is denoted by this region, that is the depletion region. Here basically what will happen is that the holes are not there. So, there will be uncovering of the immobile charges. So, this is the depletion region. Now, the electrons which are attracted by this positive terminal, they will be coming towards the insulator material, and what will happen now is that because of the presence of these electrons in the length between the two n-type semiconductors, there is now an induced n channel, and n channel is induced. N channel means the channel having the negative charges or electrons. So, what we are having now is that in between the two n-type semiconductors, which are the drain and the source, we are having now induced n channel because of the presence of the electrons which are attracted by the positive gate voltage, which are the minority carriers of the p-type substrate. So, now if the VGS is having a magnitude enough to sustain the flow of the electrons from this source to drain, then a current will start flowing, and the voltage value of VGS after which or above which the current starts flowing, that voltage is known as the threshold voltage, Vt. So, Vt is a specific voltage which is having typical value for a particular MOSFET. So, if we have Vt is equal to 2 volt, that means that MOSFET has a threshold voltage of 2 volt, that is the gate to source voltage must be at least 2 volt positive if we are considering n channel, after which only the current will start flowing. So, up to Vt, if Vs is less than Vt, then there will be no current flow from drain to source. Why current will flow from drain to source? Because it is having a positive potential. As we are observing here, we are having VDS, which is a positive potential. So, these electrons will be starting to travel from the source through the channel to the drain, and they will be flowing through this, lead to the VDS positive potential, and the traditional or classical direction of current will be from drain to source, and that current is ID. So, now ID is flowing because of this existence of this n channel, induced n channel in between the two n type semiconductors, which are the source and the drain, and this current will now flow through the source and end here. So, the drain current is equal to source current, Is equal to ID, and we also notice that Ig is equal to 0. Now, although there is a voltage between gate to source, but the current at the gate terminal Ig, that is 0, because we have seen here that there is a layer of insulating material between the gate terminal and the substrate. So, although electrons are now induced in the n channel, these electrons will be crowding near this insulator, but they cannot be coming to the gate terminal, they cannot be brought by attracting them to the gate terminal, because there is an insulating material in between. So, these electrons will not reach this gate terminal, they cannot complete the travel through this insulating material. So, there will be no gate current. The current which is entering into this MOSFET, that will be leaving this MOSFET also. So, the drain current is equal to the source current. So, here we have seen that there is an existence of an N channel when you make the gate to source voltage positive, which was not the case when we were having the gate to source open circuit. That means, we did not have a channel or induced N channel present earlier, but now we have an induced N channel by making this gate to source voltage positive, and that is why this device is called enhancement type MOSFET. That means, we are enhancing the channel or the induced N channel. Earlier it was not there, now we have enhanced that channel, we are inducing or we are making this availability of this channel. That is why it is called enhancement type MOSFET. So, this is the length of this channel, which is L, that we have earlier denoted by L, and width of this channel is actually another important parameter that is also going to make a difference in the current. So, that what we are going to discuss next. Now, let us now go on increasing the drain to source voltage, keeping VGS fixed. We are now not changing the gate to source voltage, but we are increasing the drain to source voltage. Now, what will happen? When you increase the drain to source voltage, the width of the channel will be changing, because at any point on in the channel, if we want to find out the voltage between the gate and that point, then we see that this voltage is varying, because if we are here at the source, the voltage from gate will be VGS, gate to source voltage at this point. But if we go up at any point, if we want to find out what is the voltage between gate and that point, then this is not same as the voltage which is here. So, if we go on towards up, finally reach the drain, then the voltage between gate and that point on the drain will be equal to VGS minus VDS. The voltage between the gate and the point along the channel, it decreases from the VGS, which is the voltage when the point is on the source, and then if we go upward towards the drain, the voltage will be VGS minus VDS. If we now reach the drain end, then what will happen is that the channel width, which is between the drain and the source, that channel width will be not same, it will be varying. It will be maximum, this width will be maximum when it is at the source, and if we go up, this channel width will be reducing, it will be tapering towards the drain, because the width of the channel depends upon the available voltage between the gate and the drain. Because if the gate to drain voltage goes on reducing, then the attractive force which it exerts upon the electrons to attract them, that will be reducing. So, if we travel from source upwards and reach the drain, at this point when the point is on the drain, this voltage VGD, that is between gate to drain, that is nothing but VGS minus VDS, that will be least at the drain when the point is at the drain. So, the width of the channel basically is dependent upon the attractive force on the electrons by the gate to drain voltage. So, if this gate to drain voltage reduces, that means the attractive force on the electrons also reduces. That is why the width of the channel will be reducing from source to drain. Now, if we go on increasing the drain to source voltage, ultimately the channel width will be so reducing that it will be only boiling down to a point, and that is called pinching off. So, when the channel width is just as at just a point only, it is reducing and reducing, this width is reducing and reducing as we are going on increasing and increasing the VDS, because increasing and increasing the VDS will be having an effect that this whole VGS minus VDS will be reducing, that is nothing but VGD, that is gate to drain voltage. So, if we go on increasing this VDS, the voltage between gate and drain will be reducing, and that is why the channel width will be reducing and reducing towards the drain. And if we go on increasing VDS so much that ultimately the channel width boils down or reduces to a single point only, that is called the pinch off. And at that point the saturation of the drain to source current occurs. That means the increment of VDS, if it is such that VGS minus VDS finally it becomes equal to the threshold voltage, that is called the pinch off point or the saturation point. So, the voltage between the drain to source which causes that pinch off means the saturation, that voltage is known as the saturation VDS, the VDS sat, and that is given by VGS minus threshold voltage. And what happens then? Then the drain to source current becomes saturated, and if you go on increasing VDS beyond that value, then it will be continuing to be on saturation, there will be no change. That is, the drain to source current becomes maximum at that saturation point VDS sat when this condition is met. That is, we are increasing VDS so much that the difference between VGS and VDS becomes the threshold voltage, that means gate to drain voltage becomes equal to the threshold voltage for that particular MOSFET. Then we get the pinch off or saturation point, and the drain to source current becomes saturated. After that, even though if we increase the drain to source voltage, even then it will be continuing to be in saturation. So, now we are having different reasons in the drain to source current characteristic. So, we can now plot the VI characteristic for the MOSFET. Now, before that, one important point is that the name of this device is field effect transistor, FET. Now, where from that name originates, that also has to be understood from this operation, because now we see that the VGS, which is a positive voltage, when it is applied, there will be accumulation of positive charges on this side as is shown here. So, we will be having an effect of a parallel plate capacitor. We know that in a parallel plate capacitor, in between the two metallic plates, we have a potential being applied. So, there will be positive charges accumulated on this plate, and on this side there will be negative charges accumulated. In between that is the dielectric or insulating material, that is a parallel plate capacitor's construction. So, now in this case also it is just analogous to a parallel plate capacitor, because here we have accumulation of positive charges on this side, and on the other side of this insulating material, which is a silicon dioxide, we have the electrons. So, they are like the negative charges. So, that means in between we have an insulating material silicon dioxide layer. On the both sides of this silicon dioxide we have positive charges and electrons, that means positive and negative charges. So, it is like having the effect of a parallel plate capacitor. So, there will be a field present which is vertical field, there will be a field. So, this field will be now controlling the current flow through the MOSFET. So, the current flow from this drain to source, which is because of the flow of electrons from the source to drain, that will be now controlled by this field which is present in the parallel plate capacitor being formed on the two sides of this insulating material. So, that is the name of this field effect transistor is significant, because that field is coming into existence, which is now controlling the current flow. So, now after this discussion we can now proceed to draw the VI characteristic for this N channel enhancement type MOSFET. So, VI characteristic means basically it is the characteristic between the drain to source current and the drain to source voltage with different levels of VGS. So, we have the VDS voltage and IDS is in the order of milliampere actually. So, now for different values of VGS we will be plotting the characteristic curve. Now, as we have seen that the value of VGS is important for initiating the current in the MOSFET device. If the VGS value is less than the threshold voltage for that particular MOSFET and the study, then the current between the drain and the source will be 0. So, let us for example, let us take the threshold voltage for this case as 2 volt. We are assuming we are dealing with a MOSFET device which is having a threshold voltage for say 2 volt, and we will be drawing the VI characteristic with that assumption in mind. So, Vt is 2 volt. So, if Vt is 2 volt, that means for gate to source voltage less than 2 volt there will be no current flow. So, we have say these are 5, 10, 15, 20 etc. voltages, and here we have 1, 2, these are the current magnitudes in milliampere. Now, for this reason where say VGS equal to 3 volt and onwards we will be rising the VGS, below VGS is equal to 2 volt the current will be 0. So, this line basically denotes that VGS is less than threshold voltage Vt. Now, as we rise, as we go on increasing the VGS, so when say VGS is equal to 3 volt, then there will be rise of current and it will be say this type of initially the current rise, then if we go on VDS increasing, then it will be saturation we will be getting, and that saturation voltage VDS, again we know that it is equal to VGS minus V threshold. We know that VDS saturation equal to VGS minus V threshold. So, from this relation basically we can draw the locus of the saturation value of VDS, and as VGS minus VT gives the locus of the point of this VDS. So, for when VGS is equal to 3, we are considering VT is equal to 2. So, it will be 1 volt. So, somewhere here say. So, that means we will be having basically a locus like this. So, that will be giving you this relationship of VDS saturation equal to VGS minus V threshold. So, for a particular VGS, the saturation value of VDS is this much. So, it is 1 volt for VGS is equal to 3. Now, say VGS is equal to 4, then we will be getting a saturation VDS value of 4 minus 2, which is equal to 2 volt. So, it will be say here 2 volt. We will be getting saturation at a value of 2 volt. So, say VGS is equal to 4 volt. Now, in this way it will be, if we go on increasing this to VGS is equal to 5 volt, say we will be getting and one thing to note is that the gap between 3 and 4 is not equal to the gap between 4 and 5. So, in this way it will be continuing. So, now finally say when VGS is equal to 8, then you have 6 volt as the saturation and the current is say 10. So, basically we will be getting VGS is equal to 8 volt. This voltage is 6 volt, which is the saturation. Saturation voltage means up to this voltage the current will rise, but after that voltage is reached the current will be saturated. So, this is actually the saturation region for this MOSFET. This is the saturation region for the MOSFET, and this is cut off because below this value of VGS is equal to V threshold, the device is in cutoff. So, this is the cutoff, this is the cutoff. Below this VGS is equal to 2 volt, it is cutoff, and this region is called triode region, where the current rises almost linearly. This is the triode region. So, now in this region of saturation we have the drain to source voltage greater than VGS minus VT. When these are equal, VDS equal to VGS minus V threshold, then we got saturation, and beyond this point saturation continues. Below this region here VDS is less than VGS minus V threshold, and here in the cutoff VGS is less than V threshold. So, this characteristic curve gives you the idea about the change in the drain to source current with gate to source voltage as well as drain to source voltage. If we keep one fixed, suppose we are keeping VGS fixed, we get a particular curve, and that will be giving you the idea about the saturation when it occurs, and we have seen that the saturation occurs when you have the drain to source voltage greater than equal to gate to source voltage minus V threshold. Now, another important relation actually which holds about the magnitude of the current. So, for levels of gate to source voltage greater than V threshold, if we look into this figure, greater than V threshold when we have VGS, that means the current starts rising. This is the rise of current. So, this rise of current is not exactly linear. So, basically what is happening is here is that we are getting a curve which gives you the change of the drain to source current with the gate to source voltage. If we go on changing the gate to source voltage, the current value can be obtained by a relation. So, what will be that relation? That is given by the diode, the current, the drain to source current ID is equal to K into VGS minus VT square. So, basically this is a non-linear relationship as a square is there. K is the constant which is the function of the construction of the device. K is a constant, is a function of the construction of the device. So, for a particular MOSFET device, the value of K we can know, and for a particular MOSFET device the value of threshold voltage also we know. So, the relation between the drain to source current and the VGS, that can be found out from that relation, from this relationship. And how to find out the value of K? Suppose we have known the value of the current for a particular value of VGS, then we can find out that K by measuring this VGS and ID after it is on. So, this can be found out by ID on. From this relationship only we are finding. So, ID on by this whole term, square term, VGS minus VGS on means once it is starting to conduct after the threshold voltage has been overcome. So, after this threshold voltage is reached, this is minus V threshold. So, this gives you the value of the K. So, this relation is important to get the drain to source current. Now, from this drain to source current characteristic versus VGS, we can also know about the transfer characteristics. So, transfer characteristics are the characteristic between the input and the output. So, what is a transfer characteristic? If we consider this MOSFET device, a transfer characteristic between the characteristic between input and output. Now, what is input here? We are controlling with the gate to source voltage and our output is the drain to source current. Output is the drain to source ID. Basically it is IDS, but we are generally we write it as ID, the drain current. Obviously, it is drain to source current, source is grounded. So, now the characteristic curve between this VGS and ID, that gives an important information which is known as transfer characteristics. If you are asked to find out the transfer characteristic for this particular say MOSFET device which we are having with us, then we will have to draw the characteristic between VGS and ID. So, how to draw this characteristic between the VGS and ID, that is one important thing. So, as this ID characteristic is nonlinear, as we have seen here in this relationship is the nonlinear characteristic curve. So, we will have to fit in a nonlinear curve. It is not linear, it is not enough to find only 2 points and connect, but we will have to know a number of points and connect them to get this transfer characteristic. So, that we will be discussing later. So, in today's discussion we discussed about a different transistor different from BJT, which is a unipolar device known as FET, field effect transistor, which has found tremendous use and is very popular in VLSI technology. And the particular device which is having this enormous use in VLSI technology, that is one particular type of FET that we have discussed, that is called MOSFET. And we have discussed about one type of MOSFET which is enhancement type MOSFET and N channel enhancement type MOSFET we have discussed today, and we have seen the characteristic curves and also we have known about the basic operation or physical operation of the enhancement type N channel MOSFET. And in the next classes we will be discussing about the other type of MOSFET, that is the depletion type MOSFET.